Hello and welcome back, everybody. In this video we're going to recap a little bit of the ABS and how it integrates with a couple other systems, specifically electronic stability control and traction control. The components that comprise a typical anti-lock braking system include wheel speed sensors, possibly a vehicle speed sensor, a hydraulic control unit, ABS warning lamp, and an electronic control unit. The wheel speed sensors and the vehicle speed sensor, if equipped, are inputs to the electronic control unit, and it's monitoring the waveforms coming from each wheel or each channel. As it determines whether or not a wheel is slipping, it's going to use the input data and output commands to go through the three-phase process at one or more of the circuits of the hydraulic assemblies. The hydraulic control unit, with the electronic solenoids that control hydraulic flow to the different circuits of the ABS, is going to take the command from the electronic control unit and the higher amperage power coming from fused power and go through the three-phase process at one or more of the channels of the ABS. To recap that three-stage process, it's going to isolate the slipping wheel or wheels, then it's going to reduce pressure to that circuit, and then use some of that energy stored in the system and reapply the brakes. So it's going to allow the wheel to slowly rotate and pulse that brake on and off multiple times per second in order for the vehicle to maintain some directional stability with the tire in contact with the ground, rather than 100% slip, where there would be zero directional stability if there was 100% slip. Stability control systems work in tandem with the ABS in order to apply brakes to different wheels if there is an event of vehicle stability that is being lost. And this is done through a few other sensors used as inputs to input information into a control unit. The control units used for anti-lock braking and stability control may be shared within the same module assembly. While some vehicles had electronic stability control in previous years, it was required in the 2012 model year, specifically by September of 2011 production date. In addition to performing the ABS three-phase function during a slip condition, combined with the stability control system, it's able to detect and correct understeer and oversteer conditions. The definition of understeer is the tendency of a vehicle to turn less sharply than intended. This pertains mostly to the front wheels. In an understeer situation, the driver is controlling the vehicle and intending the vehicle to turn a certain amount. Any less turning at the vehicle is considered understeer. So this would mean that all inputs to the system are intending on this direction of turn. But if the vehicle was going straight with the steering wheel position turned and the wheels turned, the sensors that are determining whether or not the vehicle is going straight or not is going to send that information to the control module. Oversteer is turning more than intended. So if the driver is intending on a certain amount of steering, oversteer would be if the vehicle is turning more than the driver had intended. In order for the control module to interpret the inputs, the sensors have to react to a few different situations. One of them is the vertical axis through the center of gravity of the vehicle, which would determine its pivoting point. When a vehicle is making a turn, there is a pivot around that center axis of the vehicle. If the vehicle is turning in one giant circle, the vehicle is doing this about the axis until it reaches the point in which until it's going straight again. That sensor is known as the yaw rate sensor, and it's usually measured in degrees per second. So degrees per second would notice the difference between this movement and this movement. So degrees per second is determining the rate at which the vehicle is rotating around that center axis, the vertical axis. As the vehicle is navigating a turn, the lateral accelerometer is also known as the G-force sensor. The lateral accelerometer is determining forces acting from the sides or laterally. It can also be configured to provide longitudinal acceleration and decel. So as a vehicle navigates a turn, depending on the speed of that turn, its lateral accelerometer is going to go towards the outside of the turn, and it's using that G-force acting on the vehicle from that direction, combined with the yaw rate sensor to make the determination or the calculation of whether or not the vehicle is in fact turning. The next sensor inputting information for electronic stability control is going to be the steering angle sensor. Now this is a calibrated sensor that's calibrated to the vehicle's alignment, meaning when we do an alignment on a vehicle that is equipped with a steering angle sensor, that sensor needs to be recalibrated after any mechanical adjustments. So marked with this piece of string notes the 12 o'clock position of the wheel. If the wheel is being turned one way or another, that's going to input a voltage into that sensor, and that sensor voltage is going to be translated into the control module as an input, determining whether or not the driver is intending on turning the steering wheel or not. When an alignment adjustment is made specifically to the thrust angle or the rear toe and also to the front toe, if the steering wheel was straight before an alignment and then a mechanical adjustment was performed and now the steering wheel is not straight, that steering wheel is inputting a voltage to the stability control module. And if the stability control module is reading a consistent voltage indicating that the driver is attempting to turn left by however many degrees, and the vehicle is not going left, and the input from the other sensors is saying that the vehicle is going straight and everything's working, the ESC light or the stability control light is probably going to illuminate or flash, and depending on the speed of the vehicle may self-apply the brakes and prevent the vehicle from traveling any further. This is a safety concern. What the module is assuming is that the front wheels are turned a certain amount and that the vehicle is not turning, which would indicate an out of control or a less than desired intention from the driver, and the vehicle as a safety feature would apply the brakes to prevent that vehicle from going more out of control. The other part of the steering angle sensor is that it can also determine the amount of torque that the driver is putting on the steering to determine how quickly the driver is intending on steering the vehicle. It can tell the difference between a gradual slow turn and a rapid fast turn. Depending on the vehicle and the system that it's equipped with, may allow the driver to disable the electronic stability control system. If disabling the system is an option for the driver, there will be a switch to disable the system. Now, if the driver switches the switch to the off position and the driver's intention is to disable the electronic stability control system, that system will be active the next time the vehicle is turned on. As a safety feature, it will always default to the active state. And if there's a problem in the system, or if the system detects a fault, there will likely be a warning lamp illuminated, and there will be code stored for whatever part of the circuit, and a code pertaining to whatever circuit it detects a fault in. The abbreviation for these systems can vary widely from manufacturer to manufacturer. Electronic stability control can be abbreviated as ESC. Other systems may include VSA, or Vehicle Stability Control, ESP, DSC, VDC, CST. The abbreviations for electronic stability control systems can vary from manufacturer to manufacturer. The bottom line is, it can be any variety of names or brand name, but if the vehicle has a system, it will indicate so on the dash for that related system. You may have to do some research in the owner's manual or in service information to determine the actual designation for the system that the vehicle is equipped with. Any vehicle manufactured 2012 or newer, or after September of 2011, will have a stability control system of some sort. Any year before that, it's optional whether or not it came with the vehicle or not. So rather than defining all of them, and there's an example of different systems abbreviated by different companies in the slideshow for this lecture. Depending on what the manufacturer named their system, however they wanted to market it, is however they desired to do so. It all comes down to integrating the ABS with the electronic stability control and sometimes traction control. Traction control is used to limit the amount of torque output from the engine to the wheels. So if a wheel was receiving too much power and was starting to slip due to more power than needed, and the vehicle is starting to spin the tires rather than an ABS stop, the vehicle stopping and skidding the tire, that wheel slippage can occur with over torque of the engine. a few methods that are used by the systems in order to regulate the amount of torque going to the wheels is it may automatically upshift to a higher gear, which will have less leverage on the wheels themselves. It may retard the ignition timing, which will in turn produce less power from the engine. Decrease fuel delivery, so less fuel is combusting in the combustion chamber, resulting in less power. Restrict the air going into the engine, which would throw the ratio of air to fuel off, and it would limit the power coming out of the engine. One thing that a traction control system will not do is shift the vehicle in and out of four-wheel drive. Before going into more of the specifics of how the system is monitoring the sensors, I want to cover a couple things with understeer and oversteer. During an oversteer event, where the vehicle is turning more than the driver is intending, the system is going to interpret all of the inputs and determine that it needs to take over control of the vehicle. And it's going to apply individual brake circuits in order to correct the vehicle from going sharper turn than desired. By doing that, what it's going to do is apply the brakes to the outside. If this is the intended turn and the vehicle is trying to turn more than the intended amount, the wheels that are on the outside of that turn, so the outside wheels, which would be on the right side of this model, the brakes on the outside are going to apply much like an ABS event where they isolate, reduce, reapply, and instead of allowing the vehicle to oversteer by applying the outside brakes, it's going to pull the vehicle back into its intended direction of turn according to the driver's input. So that's the same for left turns as right turns. So on a turn like this, if it were to oversteer this way, the outside wheels of the turn are going to apply the brakes through the electronic stability control system to where it's going to prevent that behavior from happening and apply these brakes to help pull the vehicle back into its intended steering direction. For understeer, the vehicle is going to be turning less than intended. So if the intended steering direction is this direction here, this amount, the vehicle wants to go straight or more straight or less than intended, the system is going to apply the inside brakes. So in this example, if the vehicle is turning left, the inside wheels will be the wheels on the left side of the vehicle. So if the system detects that the vehicle is going outside or is steering less than the intended direction, by applying these brakes during an understeer event will help pull the vehicle back into its intended direction. Same with the right turn. If during a right turn the vehicle is understeering, then applying the brakes to the inside wheels is going to help bring the vehicle back into its intended direction of turn from the driver. As much as I love being a talking head in these videos, I think it's going to be more important to show you some of the waveforms and the differences of how the wheel speed is being monitored for both the ABS and for the electronic stability control and sometimes traction control, and the way that those sensors operate and how to test them. Then we'll move into the Spark EV that I'm borrowing from the school and look at some of the scan tool data and monitoring some of the functions of these specific sensors in a controlled environment. And what I'll do is start with basic functions and inputs to the system and show you those on the scan tool, and then move into more combined maneuvers that take into account all of the inputs together, where not one of them is isolated from the other, but they're all being monitored together. The system will be monitoring all these inputs together all the time whenever the vehicle is in operation and the systems are active. If the system has a fault, sometimes that will disable the system from functioning, because if it can't rely on input data, then it can't accurately output commands to correct a dangerous or an unsafe condition. First, we'll take a look at the wheel speed sensor trainer and look at the waveforms that are produced by different wheel speed sensors and how they work. For this demo, we're going to be using the picoscope and the speed and position sensors trainer. On this, it has a few different types of wheel speed sensors or different types of speed and position sensors that you will find in a variety of applications. This is tailored mostly to wheel speed and wheel speed sensors. The first one that we're going to start with is this one right here. This is going to be the 2-wire analog passive magnetic sensor, or variable reluctance, or VR sensor. So it's an analog signal, 2 wires, and on our tone wheel, as we rotate this around, you will see that one of the teeth have been removed in order to provide a fault in the signal. So this tooth right here has been ground away. So we'll see that in the graph as it's spinning. So I'll bring the speed up on this, and we're reading through the signal on this 2-wire analog VR sensor. Now I'll pause that right there. So what we're seeing is that analog signal of the magnetic field being interrupted by the tone wheel, and then where the dead spot is, that magnetic field is building up, and then it's interrupted after the delay once the next tooth on the tone wheel cuts through the magnetic field. This is going to cause a spike in the voltage, and this is an AC generator, so we're going to get a spike positive and a spike negative. Then it's going to resume the normal waveform for the duration of the tone wheel until it comes back around to the fault. As the speed increases, our frequency is going to increase and our amplitude is going to increase. So the voltage coming out of this sensor is going to increase the faster we go. So frequency increases and the amplitude increases. Amplitude meaning how high and low the graph goes, and frequency is the number of times it happens per second. So as frequency increases, amplitude increases. And as I demonstrated in the GMC truck, the minimum speed recognized was 3 miles an hour. Well, the problem is with an analog signal is once you go slow enough, there's still movement occurring on the sensor, but there's so little change in the graph or the waveform or the voltage coming out of that sensor that it can't detect it accurately. So these are only accurate down to about 5 miles an hour, and in the case of the 05 GMC, its minimum speed registered was 3 miles an hour. Let's move on to the digital sensors. So these are going to be known as the active sensors. So they are these 3 different types. The first type we're going to look at is a 3-wire Hall effect sensor. So this is the one that we're going to be paying attention to right here, and it's on this reluctor wheel or this tone wheel. This is rotating at the same speed as the VR sensor was when we were barely getting a waveform. But notice how we have a strict on-off signal in a very clean square wave pattern. The difference being is we have a 5-volt reference powering this sensor. We have a ground to the sensor, and then it outputs a signal. By having a 5-volt reference voltage powering the sensor and a ground, our lowest measurement of voltage is going to be ground or 0, and our highest voltage measurement will be limited by our 5-volt reference. So this is going to operate between 0 and 5 volts. Here's 0, here's 4 and 6. So right in between that is 5, and it is right in between 0 and 5 volts consistently. This is the nice thing about digital sensors or active sensors. This type of sensor, the Hall effect style, isn't typically going to be used on wheel speed sensors. Some BMWs have used it. There are other manufacturers that have used this type, but it's not common. It's more common to have this type of sensor on a rotating assembly component in the engine, like the crankshaft or the camshaft, to monitor their positions. But typically they're not used on wheel speed sensors. With an active sensor, the frequency can increase, and it doesn't go above 5 volts or below 0 volts. So this is a DC voltage, 0 to 5 reference, 0 volts to 5 volts square wave pattern. and it's a lot more accurate and easier for a control unit to interpret the data coming in from a sensor like this. Depending on the application will depend on what type of sensor is being used. And in this case, this is a Hall effect 3-wire sensor, 5-volt reference, signal, and ground circuit going to and from the sensor. The next two sensors we're going to look at are what are named magnetoresistive sensors. These are 2-wire sensors, but they do include a third leg of the circuit. That third leg of the circuit is going to be handled inside the control module and not run out to the sensor itself. So coming out to the sensor, there will be a 5-volt reference and a signal voltage. Notice the lack of ground circuit. The grounding for this circuit, or the grounding leg of this circuit, is accomplished inside the control module. So when it comes to testing and identifying these systems, they can either act radially, which is just like our other sensors, reading a tone wheel on the radius. And this is our MR, or magnetoresistive sensor right here, reading the tone wheel. Or it can read axially. So notice the air gap in between the face of this bearing race. So this is an inner bearing race, and on the outside of that bearing race is a seal. To help illustrate this example, this is a wheel bearing that is a typical size and shape that would be installed on a vehicle. This is a non-serviceable wheel bearing assembly. One indicator on these, when you're handling them outside of the vehicle, is to bring your tiny screwdriver in contact with that surface. By bringing the screwdriver in contact with that surface, there's an attraction there, and then as you pull it away, eventually it lets go. It's a very small magnetic field. The magnetic field is actually printed into, or manufactured into, this seal that goes around the sealed bearing assembly. And if you were to put a very fine ferrous dust on this, you would see little checkers, little squares of a profile dotting the perimeter of the bearing itself along that seal. So this is what the axial magnetoresistive sensor is monitoring for wheel speed. Now, I've replaced bearings on vehicles that have these. One example is a 2003 Honda CR-V, very common vehicle. If one of these is replaced and it doesn't have that magnetic profile, then it's not going to allow the wheel speed sensor to read that profile, and it will code for an ABS wheel speed sensor. Checking them with the screwdriver when you remove them to see if it's there, and upon installation making sure that it is there as well, so you don't have that issue. Also, you may have an inner versus an outer surface where one side is not magnetic but the other side is. Paying attention to which direction these are installed will help avoid some of those issues later on, and having to remove it and reinstall it, or have to destroy the bearing upon removal and replace with a new bearing again, costing time and money for either the customer or the shop. So one of the big differences in testing one of these magnetoresistive sensors is that there is no ground circuit to the sensor. You have to go to a chassis ground or vehicle circuit ground in order to get the proper signal from the vehicle. So to check this, always consult the wiring diagram, and we're going to show the 5-volt reference circuit to this sensor. And I'm using a ground from one of the other sensors, which we can assume would be on the same vehicle. And here we're reading 5 volts, very steady. That little bit of noise in the circuit's normal to see. Now we can cut the 5-volt reference. Now we're reading 0 volts. Turn the 5-volt reference back on. We're back up at 5 volts. Okay, so now when it comes to testing the signal coming from that sensor, looking at it, it's a 2-wire sensor. So one might assume that it's an AC generator 2-wire sensor to test the circuit with both of the probes at either wire. But since this is grounded inside the PCM, we're going to leave our ground on the chassis and move our test probe from the 5-volt to the signal. Now we're going to get our high and low voltage for that circuit. Now notice that this isn't operating between 5 volts and 0 volts. This is operating above 0 and below 2. So this voltage range is going to be referred to as high and low circuit, circuit high and circuit low. It's not pulling it all the way down to 0 or ground, and it's not going all the way up to the 5-volt reference voltage. As speed is increased, our voltage stays the same. It's just the frequency that is going to change on this. And again, very accurate at low speeds. So we can have either axial or radial magnetoresistive sensors. They're abbreviated as MR. We can have digital Hall effect, which is a 3-wire digital signal. And we can have an analog or VR sensor. VR meaning variable reluctance. The variable reluctance is going to be the only analog signal, and it's going to be a passive sensor. The rest of them are active, meaning that they are receiving power and ground and producing a signal based off of what they read. They can either have a permanent magnet installed in the sensor, or that magnet can be installed in the rotating component like we saw on the seal for the bearing. So here we are at an undisclosed location with an ample amount of room around us to perform some of the functions and monitor the system and read the system inputs from things like wheel speed sensors, steering angle position, yaw rate, longitudinal and latitude accelerometer or G-force sensor. I'll start with doing the basic ones first. Since we have some understanding of wheel speed sensors already, I'll start off with wheel speed sensors. So right now on the scan tool, I'm monitoring the left front, the right rear, and the left rear wheel speed sensors. And I'm going to accelerate and stop in a straight line without changing any direction. So here we go. Test starting now. Speedometer read 14 miles an hour. So our data for the left front, left rear, right rear wheel speed sensors is reflected by being stopped, accelerating, and then stopping. They're all showing the same waveform and shows a speed of 0 at a stop and a maximum of 14 miles per hour. Wheel speed sensors are all working fine. Let's move to the next one. Next, starting with the steering wheel at the straight ahead position, I'm going to turn all the way to the left, pause, then turn back to center, pause, then turn all the way to the right, pause, and then back to center and stop. So right now we're at center, all the way to the left, stops right there, then turn all the way back to center, pause, now all the way to the right, pause there, and then back to center. Now we can review the data for the steering angle sensor. Reviewing the graph from the steering wheel angle sensor, first we did a left turn, then we did a right turn, pausing in between each of the movements. So you can see how the position changes, and this is in wheel angle in degrees, specified right here. So degrees are the units. Shows when we were stopped in the straight ahead position. Then we steered left, pause, back to center, pause, right, pause, back to center. So this is an example of steering wheel angle position, and lateral acceleration, yaw rate, and longitudinal acceleration shows some waveforms, but look at the minimums and maximums. These are very, very small amounts, but it's auto-scaling to those very minute changes. So there was no movement of the vehicle during the time of this test. So the waveforms that you're seeing are just the very little fluctuations in vehicle movement. So these are very sensitive sensors. For the next couple tests, we're going to accelerate and stop in a straight line, and then compare that to turning in a circle in one direction with the steering wheel held at a certain angle, and read the lateral accelerometer G-force sensor for that turn. So first we'll start and stop in a straight line. Then the longitudinal accelerometer will detect our G-forces while we accelerate and decel. And then the lateral accelerometer will show what the lateral acceleration is when we are going in a circle. And when we go in the circle, we'll also be able to take data from the yaw rate sensor in degrees per second of vehicle axis rotation around the vertical axis of the vehicle. Starting the straight ahead accel decel longitudinal accelerometer test. Starting now. Got an ABS event in there too. And here is the lateral acceleration and the longitudinal acceleration. This is where we accelerated, where we decelerated. All the other values are very minimal. So always pay attention to the graph that you're seeing versus the minimum and maximum that you're actually reading. So let's drive in a circle next. So now we're going to drive in a circle. We should see lateral acceleration in towards the outside of the turn. We should see the steering wheel angle held at a specific degree, pretty close to consistent reading, since I'm going to leave that at the same position as much as possible during the turn. Since we'll be doing multiple circles in this parking lot, we should see at least 360 degrees rotation around the vertical axis of the vehicle. So our yaw rate sensor will show what our degrees per second of rotation is, and I can speed up and slow down within that circle and speed up and slow down that yaw rate reading. Okay, here we go. Start off slow. There's a slight hill to this parking lot as well, so it might show a little more and a little less on the lateral accelerometer. So we've made 2 circles and I'm going to speed up. We're going 11 miles an hour now. Speed up to 14. Yeah, I can feel that. Got up to 17 miles an hour. All right, let's see what that looks like. So our steering wheel angle deviated a little bit. Had to adjust a little bit when we started going faster. So that's showing the change there. Lateral acceleration shows when we started moving and then we were holding a constant speed through the turn. And this little hump here might be reflecting the incline in the parking lot. And then we started going faster in a circle and then coming to a stop. Yaw rate, degrees per second. Minimum was 0.2 degrees, maximum was 56.8 degrees per second. So here's where we stopped. We started turning, and then it remained constant while we were traveling in a circle. So that should be expected. And then we went faster in a circle, and our value increased until we came to a stop. So that was our yaw rate in degrees per second of rotation around the vehicle's center axis, vertical axis. And the longitudinal acceleration, fore and aft, when we accelerated, and then when we were maintaining a constant speed in a circle, our longitudinal acceleration remained fairly constant until we sped up again, as opposed to our lateral acceleration, which increased as we were turning more. Now let's see if we can activate the ABS, the traction control, and the vehicle stability control, and monitor all 3 of those in a series of maneuvers. Since it's easier to break traction going in a turn, I'm going to accelerate in a turn to activate the traction control. Starting now. I felt that, and I felt it regulating the power to those wheels. Okay, let's see what happens if we try to understeer. and understeer. And an ABS stop going now. Got him. There is some interesting stuff happening here. So, watching what the ABS pump motor was doing, it activated during the turning and the acceleration. These other ones down here, anti-lock brake system okay versus malfunction, traction control system okay versus malfunction, and vehicle stability system okay versus malfunction, remained in the okay position. So let's look at some of the other information stored in the system in relation to that experiment. We're looking at left front inlet solenoid, left front outlet solenoid, right front inlet, and right front outlet. Left rear and right rear. We have right rear inlet and right front inlet. So during the maneuvering portion of this, we see that the left front inlet solenoid was activated, the right front inlet solenoid was activated, the right rear was activated, and then at the end, I put it into an ABS event where all four, right rear, right front, and left front, were all activated at the end of the test drive. Here's our steering wheel angle, lateral acceleration, yaw rate, longitudinal acceleration information from that maneuver as well. So we accelerated while turning in a circle and then went straight and slammed on the brakes to put it into an ABS event. I hope I was able to put some of this information together in a way that was easier to understand, and hopefully by isolating some of the different functions and monitoring those inputs separately, I'm hoping that that shows a little bit more consolidated information, how each of those is an input to the control module and how they all work together at the same time when we got into more of the dynamic maneuvers. So looking through the scan tool functions, reading the data, recording the data, reviewing it after you're driving it, all very helpful tools in determining what's going on in the system, and if there was a fault, where that fault might be and how to test for the faults depending on what the code is. So I hope this has been a little bit more clarifying on some of these sensors, and we'll get into more of them in the future. For now, this has been vehicle systems, traction control, ABS, and vehicle stability control. Thank you.